In this lesson, we're going to be looking at seeing if a function would be a linear function or a non-linear function. Now, with a linear function, we have two words, linear. Linear refers to a straight line. So if you were to graph all of the ordered pairs, you would see that they all form a straight line. That makes a linear function. Now, if you remember, a function is when the x does not repeat. So it has to fulfill both being a straight line and the x never to repeat to be a linear function. So first we're going to look at some graphs. It is very easy to identify whether something is a linear function by looking at the graph. You are looking for a straight line, and we're going to also look at the vertical line test. First question, is this a straight line? Well, obviously it is not, so there is no way that this could be a linear function. In this one, you can see, this one up here, by the way, happens to be quadratic, and this is called a parabola. That's going to be with our quadratic equations. The second one here is not a straight line. This one happens to be an exponential function. We'll look at that in a lesson or two, but that's not straight, so it's not linear. Here for the first time we have our straight line, and if you were to do the vertical line test, there is never a place that it would touch the line twice, so that is a linear function. This one is not, because it is not a straight line. This one is a linear function. It's a straight line, and it passes the vertical line test. It never touches the line twice. This is not a straight line, so that cannot be a vertical or a linear function. This one also is a linear function because it is a straight line, and this one is as well. So a linear function, the only time that you will have a straight line that is not a linear function is when the line is a straight line that is vertical. This kind of line is not a function. It is linear, but it's not a function because the x repeats on it. Okay, so look at this first graph here. Is this a linear function? It is. The next one is not a straight line, so it is not a linear function. So that was the first part. Identifying linear functions just by looking at the graph. That's the easy one because it's just a visual thing that you can do. You also should be able to look at a group of ordered pairs and tell whether or not it would graph as a linear function without actually graphing it. So here we have a table with 5 ordered pairs, -2, 5, -1, 2, 0, -1, 1, -4, and 2, -7, 5 ordered pairs. And what I'm going to do to check if this would be a linear function first, does the x repeat? It does not. Look at the x values here. None of them repeat, so I know it's a function, but would it be linear? To do that, we're going to look for what we call a constant change in the domain and the range. What do we mean by that? Well, we're going to start with the domain, which is the x values, and we're going to ask ourselves, what do we do to -2 to get to -1? We have to add 1. Then we go to the next one. From -1 to 0, that is a +1. From 0 to 1, that is a +1. And from 1 to 2, that is a +1. This is what we call a constant change in the domain. Each time it goes up by 1. We want to have also a constant change in the y, or the range values. So if you go over here first, we look at 5 to 2. What do you do to go from 5 to 2? You subtract 3. What about 2 to -1? You subtract 3. -1 to -4, subtract 3. -4 to -7, subtract 3. Again, right here you will see that it's the same. This is a constant change in the range. Because the domain is constant and the range is constant, we know that when we graph this, it will be linear. And we have already talked about how this is a function because the x does not repeat, so this is called a linear function. Now I need to point out to you something. When you're looking for this constant change, it has to be a number that's added, like on the domain we were adding 1 each time, or it has to be a number subtracted like we did with the range. It cannot be a multiplication or division. It has to be addition or subtraction in order for it to be a linear function. Okay, if we look at the second group here, we have, again, 5 order pairs. Check to see if it's function. Does the x ever repeat? It does not, so we know it's a function, but is it linear? Let's check to see if there is a constant change. From -2 to -1, you would add a positive 1. From -1 to 0 is a positive 1. 0 to 1 is a positive 1. And 1 to 2 is a positive 1. So this right here shows that there is a constant change in the domain, or the x values, because each time it goes up by 1. Now let's look at the range, or the y values, and see if we have a constant change. From 2 to 6, we're multiplying times 3. You could say plus 4. You could say, oh, but I'm adding 4 right here. Let's check the next one. 6 to 18 would be adding 12. So right here we see that there's not a constant change in the addition or subtraction. What you will see in this particular one, that each time if you multiply by 3, you would get the next value. But multiplication does not indicate a linear function. So that would not be a linear function, because here if you did addition or subtraction, that would be plus 4. And that would be plus 12, and so forth. So that is not a constant change involving addition or subtraction. So if you were to graph those 5 order pairs, it would not be a linear function. Same thing, let's try it again. First, check to see if it is a function. Did the x value ever repeat? It does not. So let's see what type of change there is in the domain, or the x values. This is going up by 1, up by 1, up by 1, and up by 1. So this is our constant change in the domain, or the x values. Let's check the y, or the range. Plus 4, plus 4, plus 4, plus 4. Again, you see the constant change in the domain and the range with addition or subtraction. So that is a linear function. In the next table, let's see if it is a function. The x never repeats. Let's check the change in the x. From -2 to -1, you add 1. -1 to 0, add 1. 0 to 1, 1 to 2. Each time you are adding 1 to the value. So that is a constant change in the domain. Let's look at the y. This would be a plus 4. This would be a plus 2. And pretty much you can stop right there. Once you see that it is not a constant change, you know that it's not going to be a linear function. So that is non-linear. It is a function, it's just not linear. Okay, so here we're going to look at it again. Look at the x values. It goes 1, 2, 3, 4. The x never repeats, and each time it goes up by 1. That's good. In the y values, we went up by 2, we went up by 2, and went by 2. Now I'm going to show you that when you graph these 4 order pairs, if I graph 1, 0, and I graph 2, 2, and 3, 4, and 4, 6, you will notice that it does give us a linear function, a straight line. In the next one, we notice that it's a function because the x does not repeat. We have a constant change in the x's each time it goes up by 1. What happens with the y? We go up by 3, we go up by 1, we go up by 2. This is not a constant change, so it's going to be nonlinear. So let's look what happens when we actually graph this. Here's 1, 1, 2, 4, 3, 5, and 4, 7. Notice that those order pairs, those points, do not create a straight line. It is nonlinear. So for it to create a straight line, it has to be a constant change in both the x and y values. So we've looked at just looking at a graph to identify whether it is a linear function. We have looked at tables or lists of order pairs, and we should be able to tell whether it is a linear function by looking at a group of order pairs. You also should be able to look at the equation and know whether it's going to be a linear function. Do you remember our y equals mx plus b? This is slope-intercept form, and this is going to be the form that an equation is written in for it to be a linear function. So remember, we have to put all the terms in the correct space. You want the y term on the left, then you want the equal sign, then you want the x term, and at the end is the y-intercept. So let's rewrite this first one. The x term is not in the right spot, so it's going to jump the fence and it's going to tell the 7 to move over because he likes to be in front. And we're going to do that by doing a negative 3x. So when we rewrite that, we have y by itself equals a negative 3x because it jumped the fence and changed sign, plus 7. If you can write the equation in this format, we know that this would graph as a linear function. So that is linear. If you look at the next one, you see y equals 2x squared. Notice that the x term has an exponent on it. If the x has an exponent on it, it is not going to be a linear function. This happens to be quadratic. When you have x squared, this is going to be a quadratic function, and it graphs as a parabola. So if there is an exponent on the x term, it will not graph as a linear function. How about just y equals 9? Now we're missing something here. We have the y on the left side. This happens to be the y-intercept because it does not have the x. So what is the slope? There is no slope. The slope would be 0. You could rewrite this as y equals 0x plus 9. So is that a linear function? It actually is a linear function. That would graph as a straight line because the x can be 0. Now we have y equals 12 divided by x. So again, that would look like this. Would that graph as a linear function? It would not. You cannot have the x term in the denominator. There cannot be. It would have to be in the numerator, not the denominator. That does not work. So that would not graph as a linear function. Okay, so here is a table that shows the flight data for a model rocket launch. Describe whether the data for the ascent more closely represents a linear or a nonlinear function. So we look at this. Remember, when we have a table like this, the top row is the x or the domain, and the bottom row is the y, or the range, and we need to see if there is a constant change in both. So if we look across the x values, we will see that each time it goes up by 1. Plus 1, plus 1, plus 1, plus 1, plus 1, plus 1. So there is a constant change in the x. Look down at the range. From 0 to 38 is plus 38. From 38 to 74 is plus 36. So already we know that this is not going to graph as a linear function because there is not a constant change in the y values. So if I were to graph these ordered pairs, it would not create a straight line. As the seconds increase by 1, the height of the rocket changes by a different amount each time, so this is nonlinear. So in review, we looked at 3 different things. Visually looking at a graph to tell whether it is a linear function, looking at a table, and there has to be a constant change in the x values and in the y values, and also by just looking at an equation. I was going to go back to this real fast. Woo. You should also be able to look at equation, and if it is written in slope-intercept form, it will be a linear function.